Hello everyone, I'm Zichuan Zhu from the Chinese Academy of Sciences. I'm glad to share with you our work, The Victim as the Beneficiary, exploring a Poison model to train a clean model on Poison data. Backdoor attacks are one of the most threatening attacks and can be easily executed through data poisoning. The attacker will inject the design trigger into a few benign symbols and change their labels to the attacker-defined target label. These poison symbols will force models to learn the correlation between the trigger pattern and the target label. During inference, the poison model behaves normally on benign symbols, but outputs the target label when the trigger is present. Deploying poison models can lead to serious consequences, so a secure training framework is needed when using third-party data or platforms. Defending against the backdoor attacks can be carried out from the following three aspects: data preprocessing before training, backdoor inhibiting during training, and erasing existing backdoors. Existing defense methods usually only focus on one or two aspects and are difficult to deal with complex attacks. We want to take these three aspects into consideration and build a powerful defense framework. There are two key points supporting the design of our method. And the right figure shows the first point is that we find that the prediction entropy of poison symbols in early epochs is significantly lower than that of benign ones. The second point is that strong data augmentation can inhibit the backdoor generation by distorting the trigger pattern. Based on this observation and the conclusion, we designed a dual network framework accompanied by a strong data augmentation attention mix. In our framework, we sacrifice net way to exclusively learn poison symbols and make it a poison symbol detector. In stage 2, we start training net B with filtered scalable symbols under our attention mix data augmentation. In stage 3, we adopt a supervised method to relabel special symbols and supervise the target class component in all symbol labels. The following slides will introduce each stage in detail. In stage 1, we first train NetWave for one epoch using the entire train set and calculate all symbols prediction entropy based on the output of NetWave. Then we normalize all prediction entropy to the interval from 0 to 1 and set a threshold to filter the train set. During training, poison symbols will be learned faster than benign symbols due to the similar feature of their triggers. Hence, the poison network can confidently predict the poison symbols and the target label in early epochs, causing a lower prediction entropy. In the following epochs, we only use filtered special symbols to train NetWave, allowing it to learn only trigger patterns and become a powerful poison symbol detector. As for how to choose the threshold and when to end the warm-up, we design an automatic strategy in the appendix. In stage 2, we start training NetB using filtered credible symbols. To prevent the missed poison symbols in the credible side from working, we design a strong augmentation attention mix, which only mixes the activation regions of the image. During mixing, the non-activation region of the first image remains unchanged, and the activation region is blended with the same layer of the second image. The mixing weights lambda1, lambda2, and lambda3 are calculated based on the importance of each part. For a poison network, the activation region of poison symbols is more likely their trigger locations. Mixing the activation region can destroy the completeness of the trigger patterns. In stage 3, we relabel the special symbols with the prediction from NetB and adopt NetWave's prediction to suppress all symbols labels. As shown in the left figure, since NetWave only learns the trigger pattern, separation can reduce the target class component while having little impact on the ground truth class component. We evaluate our model against the 7 backdoor attacks on 2 popular datasets, and our method achieves the best results against almost all attacks in both datasets. Even with a poison rate of 50%, our method can reduce the attack rate of most attacks to less than 1%, while maintaining satisfactory binary accuracy. In Table 3, we compare our attention mix with other popular strong data augmentations. It's obvious that attention mix has a better inhibiting effect, especially when facing stealthy attacks. In this paper, we propose a secure training framework consisting of 2 pattern networks to prevent backdoor generation from 3 aspects: filtering train data, inhibiting backdoor injection, and erasing potential backdoors. For more details, you can directly contact us by email or GitHub. Thanks for listening.